Thanks to our speaker, Martin Raum from Chalmers University for joining us. I saw on the slides it was in Swedish. Is that the Swedish version of Hochschule or something?
Yes, exactly. Yes, you're German.
Yeah.
It's still there.
Yeah. And Martin will be speaking to us, I don't see the title, but about Ramanujan-type congruences, or what was it, comparing Ramanujan-type?
Relations among them. Here's the slides. So, yes, that's what I want to talk about. It's basically the idea. I think this idea has been around for at least 5 years, more than 5 years actually. So the first time that I saw that was in Radu's papers, I think, where he simply uses these square class results to quite some effect. And so I think that is simply the idea that Ramanujan-type congruences as such are not alone. I mean, they interact. And so I wanted to investigate this problem a bit. And so what I'm going to talk about is basically the resolution, at least in the integral weight case. I think this I got pretty far there. In the half integral weight case, there's still quite a lot to do. So what I want to do is to demonstrate this Ramanujan-type congruences, how they can made accessible to modular representation theory, because that will be my main tool. And that's really where the power comes from. I mean, you first set up in quite some detail a machinery that allows you to access modular representation theory. Then you look up your favorite theorems from there, and you translate them back. And voila, you have quite some statements. And then one has to add something about modular forms. But the key is really that you make these Ramanujan-type congruences accessible to modular representation theory. And so the special case of integral weight is particularly interesting, I think, for the power that this method has. I mean, I can basically do almost everything that the method seems to allow to do. I can also do, because the modular representation theory is so strong in these cases. In the half integral weight cases, the method seems to be stronger in principle than what I can do, and I will showcase this in some computer calculations where you will see that some things hold, which at the moment I actually cannot prove that they hold in general. So this is, and then obviously I want to discuss the limit of this approach, simply because, well, all methods have limits, right? And in this case, it's pretty interesting to see that we have a dichotomy between this method and what we otherwise have in, say, p-adic modular forms. Okay, so perhaps some related forthcoming papers. Actually, so this one is very much forthcoming. I think I can send that out tomorrow. So not on archive. I first want to send it to people. So if somebody in the audience is interested in having an early copy and providing some feedback for me, that would be appreciated, just to make sure that I don't miss any citations and the usual things. The half integral weight case is a bit, I mean, the paper is basically written except for the introduction and so and the polishing. So I think this will happen this year. It depends a bit on how teaching is going. The mock data series, like the proofs are there, but the paper still needs to be written. So let's say that it happens in 2021. The idea is really that the method in the first and second paper of this series would be the same. This will be the method that we discuss here. And the method in the third paper is different, quite different. Actually, it has nothing to do with modular representation theory. Well, a bit perhaps. And I'm not talking about the details there. But I don't know whether Olivia is in the audience, but for example, in this mock data business, there was Olivia Beckwith and Olaf Richter. I had this recent paper about the Hurwitz class numbers. And this paper, the third one in this series, kind of tries to leverage some of these results. So for example, this paper with Olivia and Olaf would be one of the ingredients in this paper. So much for the overview of what I want to do. First, let me quickly recall what Ramanujan-type congruences are and some phenomena there, which basically motivates really the study, at least for me. And here, perhaps I should also say thank you to Olaf Richter, because like 2 years ago or so, I wasn't particularly interested in congruences. I mean, I had written some papers, but it was certainly not the topic that I would like think about so much as I do now. And it was really Olaf who like asked some questions, which later then resulted in this paper with Olivia, which like got me kind of ignited a bit more, actually much more than before. So thank you to him. Historically, the Ramanujan congruences, of course, are the motivation for these Ramanujan-type congruences. What I write on this slide is essentially the fact that there are UL congruences, where L will be my congruence prime. I will mostly work with primes. Many of these statements in principle have analogs for powers. And in fact, this is an area where I have not like completely exhausted the power of this approach. But for me, like the primes L were for the time being a bit more interesting, just because there was already quite something to do. So we have these Ramanujan-type congruences, and then if we restate that in terms of weakly holomorphic modular forms, then we want to perhaps first go to cusp forms, so that we can use Hecke operators to derive many more congruences. I just saw this the abstract of Nicole for next week. So this is really something I thought this in the abstract was quite interesting, in particular in light of what I'm going to say here, where I'm focusing really on Hecke operators. So the point is that you want to pass to a cusp form by isolating a subsequence that discards the singularities of the generating function here. And once you have that, what can you do? Well, you can either read Atkin or Ono, Ahlgren-Ono. All these basically use the Hecke operators to some effect to establish congruences. And it's really not so much statements about weakly holomorphic modular forms. It's really more statements about cusp forms, which was in Ken's paper also, and then of course Scott's and Ken's paper also, was really one of the basic ingredients that you needed to pass to a cusp form, so that you, in this case, could use Thea's result. So in the first case, that was Atkin, the genus zero result was important, or some genus zero methods were important, and that's why the prime here is also a bit restricted. In Thea's result, the prime is really not so important. It's it based really very much more on Tavre's density, and the role of L is really to cut down a specific image of a Galvor representation to a finite group, so that you can effectively apply Chebotarev density. And that means it's much more of a robust theorem. And that's actually also the theorem that then has been exploited in further work. One thing that one didn't, well, I think this was obvious to everybody who read the papers, it was actually never really said, perhaps, but it was once said in a, kind of said, in a MathSciNet review by Jeremy Lovejoy. But this is the only reference where I found this mentioned somewhat explicitly. But the fact is simply that these congruences live on square classes, exactly the phenomena that later Radu employed. And one thing that is even more stronger is that the congruences by Ken and Scott and Ken, they live on two square classes, meaning that actually they are not really congruences on square classes. They are concerned with the exact divisibility, in this case, by the third power of Q. And if we look then later through the theory, Stephanie Treneer, I think she was a student of Scott. So she employed the same method, extended it for the half integral weight case. I want to feature the integral weight case because that's the case that we will later restrict to. And so she could here, like, let me see. So she had this Q square. In the case of integral weight cases, you can go down to Q square. This is an interesting thing in light of some paper that I wrote with Scott and Olivia recently, where we actually tried to investigate the question, how low can you go with this Q square, Q or Q cube? We know that there's congruences for Q cube and Q4. We don't know any for Q square and none for Q either. And so we tried to investigate this result. This is a theme that will come back later in the talk for integral weight cases. But here in the integral weight cases, we at least get Q square. That's what we get. And this again comes from Thea's result. And yet again, just as an outcome of the method, in the integral weight case, if you use the Hecke operators, you always get a congruence that is basically bound to exact divisibility. Here, this Q exactly divides beta, which really means that here you get the divisibility for all n that are exactly divisible by Q. You can, but that is a kind of different topic. I just want to mention it. Of course, you have the weakly holomorphic modular form, so you project via a high enough power of UL. And then you can use the cusp form approach. That's really, I'm mentioning this one because it kind of is at the opposite end of what I'm doing. These UL congruences, you will later see in the discussion, are exactly what my new method cannot really say much about. But of course you need it sometimes, and that's why I want to mention it. Okay, so we have these things. Now, given this result by Treneer, for example, for integral weight case now, let's look at what we can actually do in general. I'm actually pretty convinced that this is known to expert. I mean, this is actually not too long of a computation, but again, I didn't find it in the literature. Here I stated only for level 1, but this is also possible for, say, Dirichlet characters. So let F be a modular form of integral weight K and level 1. And then we use the L integral Fourier coefficients, and we need that L is odd. So then if we have a prime that is not L, and we have a Hecke congruence for our F, so F slash K TP is congruent to lambda PF mod L, then we have actually two cases. In the first case here, which corresponds to having equal Satake eigenvalues, Satake parameters mod L. In this case, we have Ramanujan-type congruences actually with gap, which means that we have here this set without P set. This, of course, incurs many other Ramanujan congruences if you like raise this power here by 1. But it's really the fact that they all occur together. It's a divisibility. It's the statement that if this term here is exactly divisible by P to the M, then you have a congruence. So this is simply the fact that the Hecke operators are divisible. So if you write out the fact that the associated Dirichlet series factors, then this immediately falls out. But you have those congruences if and only if M is congruent minus 1 mod L. And if the Satake parameters are distinct mod L, then you need to factor the L polynomial, let's say over FL bar. And so here are the Satake parameters essentially. And so if you get the congruence to the m plus first power of those parameters, then you get a congruence and otherwise not. So this is kind of a complete classification, if you want to call it a classification. It's a calculation actually of Ramanujan-type congruences implied by Hecke congruences. And that will become very important because we will see that Hecke congruences are actually the same as Ramanujan-type congruences, at least in integral weight. So remember this. This slide actually gives you a full overview of possible Ramanujan-type congruences in integral weight. And with some restriction, of course, you don't want the period later. I mean, here we have isolated 1 prime. Later, we want to have more periods, and then we need to be sure that we don't hit the level and we don't hit the level. But this is quite common assumptions, and I can later explain what happens if you do hit the level. Actually, bad things happen. Okay, so we are actually, no, we have one more slide in this section. So let's actually put this question. I was already hinting it actually. We get plenty of Ramanujan-type congruences. And this is really what was some motivating question for me in several of these papers that I wrote lately. Namely, what is the precise relation between Ramanujan-type and Hecke congruences? This is something that I found exciting because it seemed to me that in the literature, only Hecke operators basically were used to derive Hecke-type congruences. And then yet nobody had proved a converse. So I wanted to know whether a converse is possible. That was really the motivation. So far, so good. Is there any questions? Then let's go to square classes. This basically enhances Radu's result. So what Radu used in his paper is the following statement, that if you have a congruence for the partition function, And here perhaps I'm a bit inconsequential. If I use beta in the paper, I would in this place use B. So perhaps B. And then we have B prime, and here we have B, and here we have B. Sorry, compulsive obsessive. So if you have this B, then you actually get a lot of other congruences where basically this B prime now satisfies this square class congruence. So this is the result that Radu proved. I think it's fair to say that this was quite a delicate argument. I mean, it was quite clever, and I think he is being admired for like pulling this argument through. Definitely by me, but also by other people that I talked to. But it is delicate to the effect that it's quite hard to generalize. So the first outcome of this new method, which I will discuss, is that this is much more robust to prove. And actually we see also the quite nice reason why this is true. So if we have a weakly holomorphic modular form, actually we don't need any any integral weight here. We can do that for half integral weight also. So on gamma n / gamma 0 n prime, and we have any finite character on gamma 0 n prime here that gives us this transformation behavior of f. And then we have the Ramanujan-type congruences here with period m and offset beta. Then for all u that are co-prime to m and congruent to this level n, where n here is only the part that occurs in gamma n, so we don't need to make any assumptions on gamma 0 n prime. This is important because otherwise you couldn't recover Radu's result. And then we have these square class results. So this has quite some nice consequences already. The fact is actually it's not so hard to prove. So if you look at the proof, I've of course not really introduced the method, but let me just say that this is actually the a consequence of the action of the split Cartan. So if you have the split Cartan in SL2QFQ, for example, or any other, the related groups, then this is really where it comes from. The Cartan here acts automatically on these congruences, and then you get more congruences automatically. And this method is so robust that it actually does not at all depend on modular forms in the sense of elliptic modular forms. So if you have Siegel modular forms or any Shimura variety and a holomorphic modular form on there with some good enough arithmetic compactification, and then you need to perhaps be careful about where the level L, where the prime here L is. I inserted this L not in 2 and 3 because I didn't want to look up the exact state of the art for integral models of Siegel modular varieties. For these, it definitely is true, but I guess you can by now also remove 2 and 3. So beta must be symmetric matrices, rational indices. M is now, instead of this integer, where we really were using m times z, the integers, we simply let m be in lattice in n and transpose like symmetric matrices of size n times n with rational entries. And then if we have this Ramanujan-type congruences here for all n in this lattice m, then we already have this other congruences where here the square class congruence is really visible in the beta. Here this TCD condition is a bit technical to spell out. For Siegel modular forms people, it's perhaps not so horrible, but I wanted to spare you that because it's not really the topic of this lecture. You can do something very similar for Fourier Jacobi expansions. So this, for example, if you have UPQ, where you not always have Fourier expansions, but only other theta expansions, then similar results hold. So this is actually quite a robust statement, as you will see later. Well, actually, I'm not going too much into the detail of the proof, but just to give you a hint of what you can do with this method. But there's a problem. I mean, if we look let's look back to this statement where we have here the square classes. I was saying that you have the coupling of 2 square classes, and here we have 1 square class. I told you this is from the Cartan. So the question that remains is, where do the other things come from? So the coupling of the square classes was actually something that I observed. I must say, I found this quite interesting when I first read Ahlgren-Ono, or actually Ken's paper. I think I read this first. I saw this gap property, so 2 square classes, and I was really wondering, I mean, if you look into the proof, it's clear why this happens, but I was really wondering about the structure of this. This was kind of bugging me because In Atkin's results, you have this single square class. So it seemed like a bit off to me, kind of special, and I really wanted to understand it. And so far, the Cartan has not provided an explanation. Actually, it cannot. It's and Atkin's congruences also show that this coupling of the square classes in general is simply not true. You will later see like what you can say about this in half integral weight cases, but let's focus on integral weight cases, because there it turns out it's always true, as I will show you in a second. So much for the coupling of square classes. Then let's look at the results for integral weights. I think now I try to slow down a bit, because so far I've mostly been revisiting what you already know. Now really the new results come. Let's see. We need an odd prime. This is more or less always the case in these results. You cannot say so much for even L. Also because, well, yeah, basically because the Steinberg representation splits for even L. This is the reason. But it nicely coincides with the fact that the Galois representations that we get from modular forms, mod 2, are also behaving in a different way. So there you see kind of complementary behavior. So we have an odd prime L, and we need here a modular form, because we will use Hecke operators. This is not true for weakly Hecke modular forms, even though one can actually use a different statement, much more technical, but one can derive an analogous statement for weakly holomorphic modular forms. So a modular form of integral weight, Dirichlet character is usually L integral Fourier coefficients. And we assume that we have this Ramanujan congruence with some period m and some integer beta. Let's see. So the first thing that I want to say, and I think this is this was making me happy, because it's really the result that I was looking for. So if we consider P divides N, and we need to make sure that it does not divide L and N. So you can find counterexamples to all these statements in case P divides L and N. And now you factor M as the P part, MP, and the non-P part, P, MP hash. So this is a P power, MP, and a coprime to P integer MP hash. Then we isolate the part of the Ramanujan congruence that belongs to not P. Why do we do this? Because I want to use TP as a Hecke operator. You can combine this result by basically gluing the result over all primes that divide M, but I find this way it's the cleanest to state it. And it implies all the other things where you combine the various P. So you have this FP, basically the congruence isolated at the P part. And then this FP is the sum modulo M of TP Hecke operator eigenforms FP lambda, and this TP actually in this associated Hecke congruence here, this one already implies the corresponding Ramanujan congruence. In particular, each FP individually satisfies the Ramanujan-type congruence of F. And as you will see, actually more, because it automatically satisfies Ramanujan-type congruences with gap. So this means when we have a Ramanujan-type congruence in integral weight, away from the level, it is automatically implied by Hecke operators. And why do we need several FP? Because it can, we saw this classification of these Ramanujan-type congruences implied by Hecke congruences. It can happen that a Ramanujan congruence is implied by several types of eigenvalues. So you can have several Satake type parameters which imply the same congruence, and then FP is actually really a sum possibly, and not necessarily an eigenform. So this for the Hecke congruences. To prove this statement actually can be proved based on the structure theorems that I'm going to show next, combining this with some more or less standard techniques from modular forms. Actually, once you have the structure theorems that I'm going to present next, and which are really then the heart of this work, this statement is quite doable. I mean, I think my proof was less than 1 page. Well, admittedly, I'm infamous for writing short proofs, so perhaps it should be perhaps 2 pages, but still, it's not too long of a proof. The structure is several results. So I've split that across several slides. And actually, these structure results, in principle, also, these all hold for weakly holomorphic modular forms. So here you can also weakly holomorphic. So this is possible, but integral weight. This is the absolute crucial thing. So the first thing is that we can actually reduce this M, and namely to the extent that basically it differs from beta by only a square-free factor. This result almost follows from the square class result, except at 2. If you have 2 divides M, then you only get 8 as here factor. So then you need to enhance this M as F. You need to enhance this by a factor of 4 if 2 divides M. But it is a statement in the integral weight case, which you can prove from what I know only through modular representation theory. I actually did not see any other proof. But actually, I'm quite happy if people tell me, of course, and if there is another proof, then you can actually remove this factor of 4 that would otherwise occur. So this means that the quotient, essentially, you can really think of this as the quotient M prime divided by beta is square free. Of course, it's more technical because you have to stay away from the level, but this is essentially the essence. This makes some computations much easier. In particular, it enables then, this is actually the first step in this analysis. I mean, this is also why I definitely need this result at 2, because only with this statement now, the fact that this is square free, morally speaking, enables the proof because it allows us to reduce ourselves later to the modular representation theory of SL2FQ for Q a prime, as opposed to some kind of local ring, where like you have Z divided by, say, Q square of Z. The representation theory of that thing is much more difficult, in particular the modular representation theory of that thing. And you don't want to do that. You want to do groups over fields, because then also, honestly, it's much more convenient. You can look it up in the literature instead of doing it yourself. The next result allows us to really conclude this gap property. And this property is the one that really enables the proof of this Hecke result. Once you have this statement, you can prove the Hecke result from before, because what this statement here with this set without p set really tells us that we have congruences on exact divisibility classes. So when in this case, MP divided by P exactly divides some kind of beta tilde that you need from, beta tilde would come from this FP, where I isolate everything away from P. So this beta tilde would then be the corresponding class on which you, well, actually not beta tilde, so let me, this should not be beta tilde, this should be N. This should be the Fourier coefficient, Fourier index of some FP, where you isolate the expansion that is not coming from P. And then if FMP divided by P, so 1 less than the Ramanujan congruence that you have, exactly divides this N, then you will have the Ramanujan congruence, then you will have this congruence. So this statement now says this result that we observed in Stephanie Treneer's work, for example, that we had this coupling of 2 square classes. Here, this is the result saying this always happens. This is not a coincidence. This always has to happen at every prime that divides M and is not, does not divide Ln. Of course, if you divide L and if you divide N, then you are in trouble. But if you don't, then you automatically get this coupling. And this is really something that one should appreciate, because in the half integral weight case, it's simply not true. Moreover, it's really the key ingredient for this Hecke result. So this is all, I mean, one could, like, I don't know. I mean, depending on the point of view on mathematics, one would say that this is equivalent to the Hecke statement that I had before, because the proof then is so easy, right, compared to what I do to prove this thing. So we have this two square classes now. And now there's one thing left, namely removing some square classes. I was mentioning before some result with Scott and Olivia. So here comes the reason why I mentioned this. Okay, so this L divides not equal to is not necessary, because I was assuming anyway that L is odd. So again, we consider this prime P that divides M. We take for granted that it does not divide L and N. And we factor M as before as MP and MP sharp. And then we have two cases where we can remove the prime completely from the Ramanujan congruence. The first case is something that you could think of an UP congruence, where here really UP, I write this down here, the UP congruence as opposed to UL, because obviously L is not P. Well, obviously, by the assumptions. So this is not saying that there's no UL congruences, because there is. It's saying that there's no UP congruences if P is not L. Which was actually something that I also, this was something that I also found quite interesting, that the square class coupling was one thing, but the other thing was that there was really no UP congruences in the literature. I found this pretty odd. Like, if there was any, then there was the possibility that, like in the delta case, they perhaps lie very far out, and the very first case would be really not in reach of the experiments that had been conducted. That was one possibility. So I really wanted to understand this, and at least in the integral weight case, we can now say, well, this does not exist. Actually, the paper contains some computations where I suggest that this also might be the case for half integral weight case, but there I cannot prove it. It's only one example computations where I reason why there's good evidence for this, but it's much more delicate there. The second thing that we can, where we can remove a prime from M is if P squared does not divide M, meaning that P divides exactly M. Then we can remove that, meaning essentially away from the level and the congruence prime, we can completely remove the square free part of M. This is really what it says. And this settles the integral weight analog of my work with Scott and Olivia, where we had to use quite different methods to analyze the partition function. This was also a very fun paper, quite intricate. There we don't get the absence of such congruences, but only a density zero result. And this is, why is that so? Because we need analytic number theory at some point in the proof. We need the large CIF at some point. And here we use algebra. So algebra has the virtue of sometimes not leaving space for density zero, and here it in fact does not. So this is the third structure theorem. This completes the results that I want to show you. After this, I would start to explain the theory of L kernels, which is behind this, or at least sketch it, and then we have some computer calculations. So if you have questions about the result, now is perhaps the perfect time to ask them. Is there any question? So then, well, let's go to the theory of L kernels. This is a concept that I wrote up in last fall, but well, I think I didn't do a particularly good job writing that paper. I don't know. I mean, I like the theory, but I made the mistake, I think, of stating things for the partition function where actually most of the results were known anyway. But they hold for every modular form. And then I didn't go to the way to really, like, for example, do what I did now with the integral weight case, and even in the half integral weight case in the second paper of the series now that I'm writing, you can do much more than I did the last year in fall there. So perhaps I guess it was really my mistake that the theory didn't receive much appreciation. But I think it's something just for the power that it has, it's worth looking at. So let's see what it is. Actually, I skipped the slide. Let's stay in order. Abstract spaces of modular forms is basically in the background. And yeah, this is an algebraic notion. Let's see, we have a finite dimensional right module for C SL2Z, so the group algebra. This is obviously a C representation for SL2Z, but I prefer to write it as modules. And then you have the kernel of the operation here. Well, obviously this should be Z perhaps. The kernel of SL2Z of V, this is simply a finite index. We need that because otherwise, well, actually we will later need even congruence types. So perhaps one should even say this should rather be congruence types. Then an abstract space of weakly holomorphic modular forms is a pair of such a module V and a realization homomorphism from this vector space V into the space of weakly holomorphic modular forms of given weight K. Here in this talk, we assume K and Z. You can do that for half integral weight 2, but then of course you have to use MP1Z. Why would one do this kind of theory? I mean, I think this is a question that I sometimes get asked if I do my funny algebraic definitions. I mean, one reason is of course that I like algebra, but the other reason is really that this is a quite common notion from representation theory. The point of such constructions is that these homomorphisms give us enough space to produce good enough models of our representations. In the end, we are interested in specific congruences here. So this is what we want to understand. The problem is that this representation might be a bit hard to handle for computations and other kind of theorems. So by allowing yourself to write it essentially as a quotient, this is like if the representation that you look at on the right-hand side is irreducible, then what you really do is that you represent it as a quotient of some other space V. And for this space V, sometimes you can find a much, much better description. This is really the reason why one wants to do this. If you do automorphic representation theory or anything like that, these things, of course, come up constantly, like Whittaker models, for example, principal series. In the Langlands classification, this kind of realization where you have every automorphic representation as a unique quotient of some principal series. This type of construction, this is a very common thing in representation theory. To make it a bit easier to think of these things, because I'm aware that I'm not talking to representation theorists, then perhaps you can think of this as the dual of vector-valued modular forms. Normally, if you have a vector-valued modular form, you have a function that on the upper half plane assigns you a vector. And quite often we write this as a vector with components, which means that we choose a basis for this space. But in principle, it's really just like taking the image in some vector space. And here we really do the opposite. We pick some vector and we assign a modular form to this. So in particular, if you have a vector-valued modular form, then picking a component, the fact that you pick a component would automatically give you an abstract space of modular forms, which is then the space of components of that vector-valued modular form. And the easiest case, of course, is the quite hilarious CF and identity. This is a hilarious modular form because it showcases how one should not do mathematics, introduce fancy notation for simple things. But it turns out actually this thing is the first ingredient for several constructions. And the reason is simply because, after all, we are interested typically in these statements in Ramanujan congruences of a given modular form. We not so often ask for modular forms of a given representation type. This happens perhaps in moonshine or so, but here in this topic of Ramanujan-type congruences, we typically have a modular form. And so then the CF identity perhaps looks a bit more friendly to you. Yes. The L kernel. So now we have the abstract space of weakly holomorphic modular forms, and we need to associate yet another object because so far we have only worked over C. And so certainly there's no room for congruences here. The L kernel, written curl FEL, so free expansion, that's what FE stands for, of our V phi, is the submodule of all vectors here that map to weakly holomorphic modular forms with L integral Fourier expansions. So this is a module a priori because you can add things. It's a module over, let's say here, I've written it here. You can, for example, take the L integers in Q bar. Obviously, you wouldn't want to do that because later you want to work rather with number fields. But in principle, you can, and also for congruent subgroups, this doesn't make sense to do this. So one always would use a number field, I think. But let's think of Q bar here for simplicity. Then I don't need to fix a number field. And the very important fact is, and this needs a proof, the proof effectively is 400 pages plus 1 page, 400 pages written by Deligne and Rappaport, and 1 page written by me. So it's really more or less, it falls out of Deligne and Rappaport in more or less the same way as all these statements fall out of Deligne and Rappaport or cuts. So the first time that you see this kind of statements is in Jochnowitz. She didn't seem to use, well, she didn't need for her purposes Deligne Rappaport. And I think Radu always cites Deligne Rappaport. So, and here there it is.
So Martin, should we think of this as some kind of Q, basically the Q expansion principle then, or?
It is basically a Q expansion principle, yes, but with the divisibility added.
Okay.
So here, for example, if this L here happens, then you can give an estimate for how divisible another Q expansion is. So like perhaps this is, so if in weight 2, I think you can gain at the most 1 divisibility by the prime in the level. When changing to another custom. Deligne and Rappaport have worked that out quite explicitly. In higher weights, you get higher divisibilities. But as long as you are here in this gamma 0 L to the M, well, actually L to the M is simply the highest divisor of the level. That is a power of L. Then you actually preserve divisibility. Does this answer the question?
Okay. Yeah.
And I think this is really a good remark because we know that the Q expansion principle is quite powerful. And here this actually leverages this simply. The Q expansion principle behind this now receives a bit more structure, namely it is now a representation. This is really the observation that is enabling all this. Before we were always using the Q expansion principle, like here comes some element of SL2 or MP1, and then we do the transformation, we calculate it explicitly, then we have another element and do the representation. But representation theory simply allows us to say, okay, this is a vector, what a representation does it generate? Which is really then later the game that you play. We need one more ingredient. Sorry for that. The people who read my papers will actually know these things. I mean, actually, not everything on these slides is completely new. These Hecke operators, these vector-valued Hecke operators, I introduced in a, I think, 2014 paper. Or at least I think I wrote it 2014. Oh, I'm pretty sure I wrote it in 2014, but perhaps it was published much later. And here, this is a dual thing. So the vector-valued Hecke operators at the time were for vector-valued modular forms. I needed that to compute modular forms. Now the dual is to study modular forms, basically. Tm of V here is defined simply as the tensor product. Strictly speaking, perhaps you want to have an induction here. I don't know. I don't know. I mean, both things. I mean, after all, they are equivalent. I preferred this tensor product notation here simply because it's much closer to modular forms. Namely, then if you want to realize this V tensor gamma, you do something very unexciting. You take the realization of V and you apply gamma. So this is, in some sense, this is a very unamazing way, but it actually turns out to be quite powerful, as you will see in the next paragraph. I'm just saying that to like really emphasize that you shouldn't be afraid of this. So this gamma is a typically, I mean, typically this would be A, B, 0, D, for example, and then you slash your modular form with that. So this is something that is quite doable and quite explicit. Like, let me. Okay, but why is this a good idea? Well, first of all, we will see in a second that it encapsulates Ramanujan-type congruences. But from a representation theoretic point of view, this is also a very good object. And that really is the important part, because as I told you several times now, I'm going to use representation theory. So if this thing characterizes or like gives us a possibility to characterize Ramanujan congruences, and this thing also allows us a description in terms of representation theory, then we are like in a good position to later use this Ramanujan, to use the representation theory, because the game plan then will be to take a Ramanujan congruence, get some vector in this representation, use the structure, use what I'm going to say next, and like derive other vectors in that representation by virtue of modular representation theory, and then translate it back to Ramanujan-type congruences. So what is this amazing fact? I mean, it's actually really simple to prove, but it's still so amazing because it makes our life so beautiful. The induced representation of gamma 0 m from gamma 0 m to SL2Z of a certain pullback phi m is a certain map from, well, actually, this is phi m, and this is not the usual inclusion. So this is, what do you need? You need, you want to multiply it here. So gamma up 1n. So it's this map here. So it's kind of a twist. This kind of things explain from a purely representation theoretic point of view, for example, why you change the character if you apply these Hecke-like operators like v, vp or up. This twist, this phi m, or the pullback actually associated with it, that one explains why then the Dirichlet character also changes. Or, well, not the Dirichlet character, but in this case, the character that is associated with the eta function changes. So we get we get this pullback. This is now, this V was before, let's say, a representation for SL2Z. Then we pull it back, then it's a representation for gamma naught m, and then we induce it. And this one injects into TMV. Actually, one can really precisely describe the image. So the image is the so-called, or what I call the primitive vector valued Hecke operator. Quite fairly explicit, simply the at the condition that that I write it up here. So Tm times, this is the primitive Hecke operator. This would simply be that the GCD of the entries here, or the content of this matrix, this is also another word you say there, is 1. So for example, A, B, D in this example here, they should be co-prime. So a relatively hands-on description. So once we have this, we are in very good shape because we have an induction from gamma 0 m of some representation. This representation phi m of this vector, in the cases that we look at, can actually, through a trick, made to look like something like a trivial representation. Obviously, it's not the trivial representation in general, but using a specific trick. This is, by the way, one of the reasons why we need integral weight cases. This trick only works in integral weight cases. So using that trick, we can make this look like a trivial representation. And that means, in the lingo of modular representation theory, that we are now in the principal block. The principal block is essentially the Steinberg representation and then one or another vector, but it's really the Steinberg representation that we are looking at now. And this is why, for example, I would now claim that Ramanujan-type congruences for integral weight modular forms are governed by the Steinberg representation. This is really the upshot of this work, I think, at least from my perspective, that of course with all this machinery, you can eventually reduce it to something which is inherently linked to the Steinberg representation. As I was saying, I know that there's probably no representation theorists in the audience, at least not too many. So I will spare you the details of what exactly the principal block means and what the modular representation theory is. But with these keywords, if you Google that on on Math Overflow or so, you find quickly something that should give you an impression of the theory that happens there. Or actually, one can use this book. There's a book on the representation theory of SL2FQ by Bonafé. I honestly remember this sometimes by thinking bon café, which means in French, good coffee. This way it's very easy to remember this name. Anyway, he has written a book there. You can also read up on some of these modular representation theory aspects if this connection and these applications have ignited your interest. There's only one more thing to say about, sorry, about this theory, namely, what is the key method now? Well, I was hinting that before. The Ramanujan-type congruences that we have for, say, F, which is a realization. For example, here we could use simply the CF, so example given, use CF, comma, identity. So then you immediately get a realization for your Ramanujan-type congruence. But in principle, you can use it for other things also. That corresponds to a specific vector, which I call TM V beta. So basically the Hecke image of this vector V with shift beta. And this is a vector inside of TMV. And now the question is, which representation is generated by these TMV? And which TMV beta prime in particular does it contain? This is good enough to prove the coupling result. It is not good enough to prove this result about the square freeness of m divided by beta. And it's also not good enough to remove p from the, remove the square free part from m. There you need to ask a bit more than just these vectors. There you have to go into the details and check what other vectors lie in that representation that is generated, which is possible. I've done it. But it's quite tedious in some points. So this part of the proof, this proof is a relatively technical proof, in fact, with something like 5-6 pages or so. And quite some of the effort made there goes into the vectors that go beyond this TMV beta prime. This is it, yeah. And the point is that this is actually modular representation theory, simply because whenever you have this OL, let's say actually OQL, this is basically OFL, and then tensor, some other module. Oh, no, certainly not R. Sorry, this was a typo, a Radu, but I don't want to leave this here. This is too embarrassing. Let's write some ring R. Ah, no. Nah. So now there we go. Some ring R. So it's really essentially modular representation. This is as much as I wanted to say about the method. I mean, the problem is really that the paper very quickly goes into representation theory. And before that, you have some actually not too enlightening. I mean, the fact that these Ramanujan-type congruences correspond to certain vectors, this proof is, I mean, you can do that. I mean, it's a computation, really. It's not very enlightening to discuss this. So I think here, at this point, there's not so much to discuss for this method, except if you want to go into representation theory. So I wanted to do something else instead. Namely, I wanted to show you one example computation that I was already announcing, and an example computation in the case of half integral rate modular forms. Oopsie, this is that. So let me see, what do we want? We want this one. Where's my, there we have this one. And oh, I forgot, sorry, in my interface, I forgot to put this thing after restarting on all desktops. So here we have this. So now, and then we want the shell. You can also see me now. Perhaps this makes you feel better. And then we swatch. So what do we want to do? You see some code here. This is some advertisement also. This code depends on modular forms. Actually, when preparing this talk, talk, I saw that this this module now has more than 40,000 lines of code in Julia, which is actually a relatively dense language. So this is a relatively extensive package whose purpose is mostly to compute vector valid modular forms, in particular also Jacobi forms. Later, I want to implement Siegel modular forms, so I have an implementation strategy for all these things. So this all should go in there. At the moment, it's not quite released, also because one of my students, Tobias Magnusson, perhaps I write his name here. So Tobias Magnusson, I actually don't know whether he's in the audience. He might be. So this guy is quite talented, I think. So, and he has written parts of his PhD thesis on this topic. So we first want to write a paper about that, and then we will release this. This is all open GPL and whatnot, but we just need the time to write the paper and actually speed up one thing. There's one part of the code which is at the moment a bit slow. We know how to speed this up, but it will take a while. Anyway, what do we want to do with this code? We want to, actually I don't need to go through, I have already loaded this code. Normally you would like copy this over to the command line, but I've already done that. Among other things, because Julia, if you don't know that, that is a just-in-time compiled language, and I have not pre-compiled any of this code. So by just copying into the Julia interpreter, I pre-compile it on the fly, which makes this demonstration a bit faster. We want to investigate modular forms, a cusp form, let's say, of weight square, 13 square minus 2 divided by 2. This is the weight that you get if you isolate the square classes from, say, the partition function mod 13. This is what happens if you apply the UL operator. Obviously, you can go down in the weight, but let's stay with this weight. We can also do this with the other non-square class, with the other square class where you get possibly a cusp form. Then the weight is actually the same mod 24, and this mod 24 is the only thing that counts for what we are going to do because of representation theory. So then our m, which is the capital M here, I use lower m. This is 11 to the 4th. We want to investigate the Ramanujan-type congruences on the modulus 11 to the 4 for this cusp form, which boils down to evaluating what happens for the partition function on 13 times 11 to the 4. This thing in particular includes Atkin's congruence. And here we want to simply pretend that we have a congruence here. This basically does this minus 1 over 24 thing that you always have to compensate for in the partition function. This line just does this. And what really it comes down to is that we have a divisibility of what you would often call B minus 1 over 24. This one is divisible by 11 to the 3, exactly. So this is what this line does. And then we generate an arithmetic type. So this is a specific representation because it's an arithmetic type, meaning it's associated with vector modular forms. We have to take the dual. I was already saying that abstract spaces of modular forms are duals of the vector valid modular forms, and the notion of arithmetic types is associated with this. And now we create this Hecke operators. This takes actually a while because it's actually something like a 17,000 dimensional representation. We can check that in a second. It's quite, yeah, impressive kind of. So now it's done. Let's actually quickly check the row Hecke. This was quite large. Hecke, come on, yeah. So, 15,000 only, sorry, I was exaggerating. So because this is an unreasonably large thing to do over the cyclotomic fields, we do this with modular representation theory, then everything is faster. Here in the next line, we basically provide a free module on which this representation acts. I mean, one could implement this a bit nicer, and probably at some point I will also do. This generator images are simply an efficient way of implementing this action. Again, one could probably implement it nicer, but because this code is not published yet, then you kind of see what happens, namely people write the code that works for them. Then this does not exclude myself. So this Hecke vector B, this is a function that is this is basically the function that generates the T sub m of V comma beta. This is the analog now in this code. I just define it as a general function because I later want to use it for other things. Here I generate basically the module which is spanned by this vector. And the next code is a bit unintelligible, probably on the fly, but what it does is it generates the representation. So you now compute the representation. This is kind of an orbit algorithm that is computed only in linear algebra. Again, this should be implemented in general, and I think I will do that at some point. Actually, this kind of code belongs into abstract algebra, which is one of the frameworks that I use in the background. It takes a while because it's not super efficient, and it's also a very large representation. I have not profiled this code. It's fast enough for my purpose. So now it's done. So now we have the representation that is generated by this congruence, which actually does hold because Atkin's congruences hold. And so now let's go through this loop. We have simply a non-square, and then I printed that for a large effect there. So this is not a congruence on the square class of 1. There's none on 2. There's none on 11. 2 times 11 not. Also for the squares, none means there's no Ramanujan congruence implied automatically. So this framework means that one Ramanujan congruence might imply others, and we know anyway that we can focus on square classes from, say, Radu's result. In this case, it would totally be sufficient to use Radu's result. So the only thing that we are asking for is on what square classes do we automatically get a congruence? And the point that I want to make is there's 2 square classes. We started with 1, but the representation theory automatically in this part tells you that these things are coupled. And now why did I use this example? Because this is exactly the situation of Ono and Ahlgren-Ono, where they have these 2 square classes. And you would wonder, given the method of the proof, you have this Hecke operator and it automatically falls out. But if you ever found a modular form that had such a congruence, you would, by the virtue of representation theory, oh, actually, I see. I'm actually should take out this video because you didn't see what I was marking. So by virtue of representation theory, you automatically would get both square classes, exactly as in the paper by Ken. So this is not an accident of his method or anything. This is simply a truth universally for these types of modular forms. But then on the other case, as I said, in Atkin's results, for example, we don't have this coupling of 2 square classes. So it actually depends quite delicately on what power of the prime q you have. So if you put in here m equals q to the 3 and beta exactly divisible by q square, then you don't get this. Then you don't get this coupling of square class. So it's quite different. I think I went over time by basically 2 minutes. Sorry for that. Well, I hope this was intelligible. If there's any questions, I'm happy to answer them.
All right. Well, thank you, Martin, for a fascinating talk. Yeah, I have a question, but I'll ask if a few people are clapping. Yeah, let's clap for Martin. All right. Anybody else have any questions?
I have one that's maybe more of me not understanding everything going on in the representation theory. So Boylan has a paper where he looks at Ramanujan-type congruences for powers of the partition function. And there's a nice family that's essentially can be explained by certain powers of eta having complex multiplication. And then he notes that there's others that he calls super exceptional that seem kind of like sporadic and can't maybe be explained uniformly in that way. Can your method see the difference between those 2?
No, unfortunately not. These are all kind of UL congruences. So they escape this power. And the reason is really this gamma not L to the M. So the only extra action that we get is there the Cartan. And the Cartan does not provide more than these square class results. And well, the square class for UL of congruence is even trivial because you have the trivial one. So there, unfortunately, I cannot say so much. This is, yeah. I mean, I wish I could say more about that. And at some point, I was naively optimistic. But for these things, you need other methods. Yeah. And I think this is a very good point to bring up the CM forms also, because there, of course, you have automatically the level. And then L divides the level, and then the theorems that I stated also don't hold. So what I'm certainly not claiming that my theorems are exhaustive when it comes to what congruences are interesting. I mean, I think that would be very far from true. But when it comes to how far this method goes, many of these things are exhaustive. So one could, if you didn't have this UL congruences, so this, because of that we are out already. But in the case of CM congruences, you can do a bit more because there L divides the level, and you would hope, well, actually you can produce more. But the point is, you had this keyword, principal block. So the problem is that you don't get into the principal block. You really get into supercuspidals, mod P. That's a difficult topic. So I would not even dare starting such an endeavor to, like, perhaps in the square free case you can do this. But beyond that, you cannot do much simply because these supercuspidals are so complicated. And you automatically land in such areas because then the level, if you have a new form of deep enough level, that's automatically what you land at.
Yeah, that was essentially my question. I guess the broader question is what congruences in the literature are sort of explained by this. I guess to follow up on Ian's question, if you look at the k-colored partitions and k is even, it is an integer weight.
Yeah.
So I guess in that situation, there are many congruences there that you've proven cannot come from Hecke operators, so they must come from something else.
So no, I mean, they come from Hecke operators automatically. In even weights, they automatically come from Hecke operators, except if these are these UL-type congruences, or if you are at the level. So if you are, say, L is not 2 or 3, and M is also co-prime 2, or yeah, not co-prime because you want you first need 1 power of L to remove it, remove the principal part. But apart from that thing, you do the typical thing that Ken did in his paper to produce congruences. All of these actually come from this source. There's no other source. Or, well, if there's another source, actually, perhaps one should formulate this in a different way, because of course there could be another source. But then my theorem tells you this also comes from Hecke operators, and that could be an interesting statement about these other sources. For odd, like one thing that I was also interested in is the delta function. I mean, in the literature, of course, the UL congruences are the famous ones, but there's no UP congruences or anything like that, no Ramanujan congruences for the delta function, apart from the silly ones that you get from the Hecke operators. And well, there is no. This is also one thing that I wanted to know.
Mm-hmm. Okay. Yeah. Any other questions? All right. Well, if not, let's thank Martin again. And I guess the video, the slides are already online, and the video will be on the YouTube channel probably later today.
Yeah, the slides aren't quite online yet, but they will be in probably 15 minutes. And yeah, I'll send out in a day or so an advertisement for Nicholas Allen's who is I believe he's speaking next week. Let me check the. Oh no, we currently don't have a speaker next week, so there's potentially we're waiting to hear back from some people. So Nicholas is the next scheduled one on September 8th, but I'll email everyone to try and keep them updated if there is one next week.
Mm-hmm.
Great. All right. Well, if there are no further questions. Oh yeah, I can.